Alright, here we go, the final push. So chapter 7, and 8 and 9 is kind of where it all starts coming together. So let's review this real quick. There are two types of distributions. There is discrete and there is continuous. Now there are several distributions. We've only talked about three. The discrete distribution we've talked about is binomial. Okay, so for binomial, x is some random variable, approximates a binomial distribution. Binomials parameters are n and p. N is the sample size and p is the probability of it happening. So you gotta remember p and q. So binomial, there's only two outcomes: a success or a failure. P is the chance of it being a success. Q is the chance of a failure. And discrete, you gotta remember, discrete is countable. Discrete is a whole number. It can never be a number in between. So you're surveying people, 50 people. If they're happy with their marriage, you're gonna have a whole number of answers. You're gonna have 43 are happy, 7 are not. You're not gonna have 43.5 or. It's always gonna be a whole number. Continuous distributions, they include the numbers in between. You can have an average test score of 72.5%. So if you can go in between, it's continuous. So they're kind of like measured things. We've got uniform and we've got the normal. Okay, the uniform, x is some random variable, comes from a uniform distribution and its parameters are a and b. Okay, now here's what we got to remember about a uniform. Uniform, if we've got a number line, a is the smallest, b is, so it's kind of like the range. It goes anywhere from a to b. And if you graph it, it is always going to be rectangular, and the area under the curve is 1, or 100%. 100% of the data fall under that curve. Okay, normal, this is where we spend 95% of our time. X is some random variable. Well, it approximates a normal distribution. Its parameters are mu and sigma. So mu is the mean, the population mean. Sigma is the population standard deviation. So you got to remember the difference between population and sample. Population is talking about everyone. So if we're talking Delta High students, the population would only be 400 to 500 kids. But if we do a sample, if we survey the freshmen or something, then it's 130 kids. So if you're taking a sample of the population, but if you're talking about smokers, the population is every smoker in the world. And if you want to take a sample of people who smoke, then you take a portion of that population. Okay, so populations can be everyone on Earth, or you can narrow it down to the population of just kids at Delta High. Okay, and you gotta remember this. Normal, its graph is a curve, and the area, just like the uniform distribution, area under the curve is equal to 1. Now, central limit theorem is way cool. Central limit theorem says, okay, if we're looking at a population and the distribution that describes it may or may not be known, if the size of samples is large enough, then the distribution of the sample averages, that is x bar, will be approximately normal. So you know three distributions: normal, uniform, binomial. There's like exponential. There's several more. There's several types of distributions, way to describe populations. So this is pretty cool because it says it does not matter what distribution is used to describe this population. If you take a sample of it, but your sample's got to be decent. If your sample's big enough and you look at the averages, the sample means they will always approximate a normal distribution. So you got to go x. Let's do the normal distribution, so that's mu and sigma, versus x bar, and that's what this is trying to explain. So x bar, you're taking the averages, the sample average, and it's going to approximate a normal distribution. You use the exact same you use don't use the sample mean, you use the population mean. So the mean of the sample means will equal the population mean. But your standard deviation, so you got to remember this. Mu versus x bar and sigma versus sx. So x bar is the mean from a sample, sx is the standard deviation from a sample, sigma is the standard deviation from the population, mu is the mean from the population. So you're not going to use standard deviation of the sample, you're going to use the standard deviation from the population, but it's going to be smaller. You're going to always divide it by the square root of n, how many people are in your sample. Okay, so that's maybe, I'm sure you got it memorized by now. This definitely is good to put on your note card. Calculate a z-score. Take the x bar, subtract mu, divide it by that, and that will give you your z-score. And standard deviation, you already got that. So we're in business. Okay, here we go. So let's revisit some of the problems we did from your homework. Hopefully these bring back good memories, and it should be the second time you see them. And on that, they're probably going to pick a few of these and put on your final, hopefully. So it'll be good to revisit them. Okay, 65. The length of songs in a collector's iTunes album collection is uniformly distributed from 2 to 3.5 minutes. Suppose we randomly pick 5 albums from the collection, and that sample contains 43 songs. So here's what we got. Okay, well, I guess let's just go through A, B, C, D, E, F. A. Okay, what is X? Now, maybe let's start with B. X, this is a uniform. They're uniformly distributed. So X is coming from a uniform distribution. Okay, uniform distribution is A to B. A is the kind of the min. So the smallest song is 2 minutes, and the longest song was 3.5 minutes. So there we go. Now you gotta have this in your notes. You've got to remember some things about a uniform distribution. So if we go 2 minutes to 3.5 minutes, we need the average, and the average is just halfway between them. What's halfway between 2 and 3.5? You just add them up. 2 plus 3.5, so that's 5.5. Divide that by 2. 5.5 divided by 2, you should get 2.75. So halfway between here is 2.75. So the average song is 2.75. Okay. So you're also going to need, on your note cards, there was a formula to find. So this one's kind of common sense-ish, but this one is not. The standard deviation. The standard deviation is this. It was the square root of b minus a squared divided by 12. So that will give us the standard deviation. Okay, so we're going to go square root of 3.5 minus 2 squared divided by 12, and that gives us 0.433. So now we kind of know the average song length, and we know the standard deviation's 0.43, so almost probably 25 seconds or something. Okay, so now we're ready to go. So in words, this X, what is X? X is, okay, it's a length of songs. It's not the average length of songs, it's just the length. X is length of songs. That's what we're measuring here from some collection. So we measured all these songs and we found that the smallest length was 2, the largest length was 3.5. Okay, so X could be anything between 2 and 3.5. Could be 2 minutes 5 seconds. Could be 3 minutes and 10 seconds. Who knows? So it could be any of these numbers. Okay, so we've already got the distribution set up. Okay, now in words, what is X bar? So there is a huge difference between X, the random variable from that distribution, and X bar. So X bar comes from a sample of the original distribution, and X bar, now we're talking about the average length from that sample of average length, average song length from the sample. So X is just talking about the length in general. But X bar, we're talking about the average length. And because we did a sample of 43, that's large enough. It's going to follow, the average is going to follow a normal distribution. So here we go. X bar is going to be normal. The mean, you use the same mean as the distribution mean, and that is this 2.75, and you take the population sigma, so that is the population sigma 0.433, and you divide it by the square root of 43. Okay, E, find the first quartile. Okay, so this question is awesome because it reviews kind of everything we've learned up to this point. So the first quartile, you got to remember like your box and whiskers. So this is like the max, this is the min, then you got your box. This right here is quartile 1, this is the quartile 2, which is the median, and this is quartile 3. So 25% of your population lives here, 25 lives here, 25 lives here, 25 lives here. So this is the dead middle, this is the median. Half of them are below, half of them are above. So the first quartile, here's what we're going to do. Okay, we got to go calculator. Okay, you're going to go, once you get everything set up, you're going to go menu 6, 5, it's a distribution, and we're going to inverse the normal. So I want to know what's at that 25th percentile. So the area, I'm going to type in 0.25. The mean, we are typing in 2.75. And the standard deviation, we're going to type in, okay, we're going to type in this. The standard deviation was 0.433. Divide that by the square root of 43. Okay, and hit enter. Okay, so 2.705. So at the 25th percentile, now let's see if this even makes sense. So right here, 2.705. And now this is from the sample, so this is from the averages, so it's going to be a little tighter. So 2.75. Gosh, does that make sense? First quartile, average song length is 2.7. Oh, no, what was it? 2.705. Okay, so that means, God, because look at your original distribution, and we're kind of not looking really at the original, we're just looking at the sample. The original, the average was 2.75, and this is saying the first quartile, so from here, 2.705. The smallest is still going to be 2 minutes. 25% of them live in this range, from 2 minutes to almost 3 minutes. Okay, let's keep going. Let's look at the IQR. So the IQR is this. The IQR is the difference in this box. It's the difference from quartile 3 subtract quartile 1. So we need to know quartile 3, and this will kind of give us a feel if we're right. So let's go menu 6, 5. Let's do the inverse normal. Now we want an area of 75%, and the mean we're going to use 2.75. Standard deviation we're going to use 0.433 divided by square root of 43. Let's see, just 0.4. I think I got too many 3's in there. Okay, let's hit enter. Let's see what that says. Okay, so this, we're probably in good shape. So this one's 2.79. Okay. So right here is 2.79. Okay, I think we are in good shape, because look, kind of the middle is 2.75. So 2 minutes, 2.705, 2.79, and the middle is going to be 2.75ish, so we're okay. Now, I'm going to take this quartile 3, subtract quartile 1, and we should end up with 0.09. Okay, that's a good problem. Let's look at 69. The distribution of income in some third world countries is considered to be wedge-shaped. That means there's many very poor people and very few middle income, and then even fewer wealthy people. So suppose we pick a country that has a wedge-shaped distribution. Let the average salary be 2,000 per year with a standard deviation of 8,000. So the distribution, it just says it's wedge-shaped. It doesn't say what was it, a normal, binomial. It doesn't say what it is. It just says kind of the shape of it. Okay, but they do give us the average salary and they give us a standard deviation. So you're randomly going to pick 1,000 people from that country. So here we go. What is the difference between x and x bar? So x is the original distribution. So x is going to represent the salary. So it is the salary of people from this country, from a third world. Doesn't tell us the country, does it? No, suppose we pick a country. So we're gonna start asking them, hey, what's your salary? What's your salary? What's your salary? That's what we're measuring or counting or whatever. Salary of people. Okay, now x bar, that's gonna be the average salary of the sample. So x is just measuring salaries, but x bar, we're gonna sample 1,000 of these people, and we're looking at the average of those people. So the x bar, here we go. Now when we do these averages, that indicates you're going to use central limit theorem, and it does not matter what the original distribution was. The central limit, once you start doing averages, it's always going to be normal. So we're going to use the population mean, so that's 2,000, and we're going to use the population standard deviation, 8,000 divided by the square root of 1,000. Okay, so now D. How is it possible that the standard deviation is greater than the average? Because most of the time, I mean, look at this guy right here. On the songs. So your average was right in the middle. Your average song length was 2.75 minutes, and our standard deviation was almost 0.5 of a minute, so it's almost 30 seconds, 25-ish seconds. So usually your standard deviation is much smaller than your average, but this right here says the average salary is $2,000. So if we start looking at it like this, so we got $2,000 here, and if the original was normal and the standard deviation was 8, then the next standard deviation over here would be like 10 grand, and then it would be 18 grand, and then 24 grand. No, not 24, 26. But then look, if you go a z-score to the left, it's like 2 grand minus 8 grand. So minus 6 grand. But it doesn't say the distribution is normal, but that's a good question. How come your standard deviation is so high? And the answer is, I mean, they kind of explain it. You have so many poor people. I mean, they're making maybe $100 a month, $200 a month, $50 a month. So the majority of your sample is going to be making nothing. But then if you have one or two, if you have a few wealthy people, that jacks everything up. So if I throw someone in there that's making 100 grand a month, that's going to really screw your standard deviation up. Okay, now E is the question we need to focus on. E is the one that makes it good. E could be a final question. Okay, why is it more likely that the average of the 1,000 residents will be from 2 grand to 2,100 than from 2,100 to 2,200? So what they want you to do is find the percent of this happening. So what's the chance that the average falls from 2 grand to 21 grand? So here we go, E. Alright, what we're going to do is this. So it's calculator. We're going to go menu, 6, 5, and we are going to use a cumulative distribution. Okay, the lower bound. So they want us to find the range from 2,000 to 2,100 using that population mean of 2,000. And okay, for sigma we are going to use 8,000 divided by the square root of 1,000. Okay, so that is going to return, that's like a 15% chance. So really here's what they're asking. They're asking this: what is the chance that the average is going to fall between 2,000, going to be greater than 2,000 but less than 2,100? And what is the chance that the average is going to fall from 2,100 to 2,200? So we just did this one and we got a 15.4% chance. Whoops. Where are we? Alright. 0.154. Okay, now if you do this one, so if I just go up and copy that and hit enter, I'm going to change this from 21 and change this to 22. That is a 13.2. So that is 0.132. So this has just 2% chance higher. It's got a little bit better chance, not much, but a little. So why is it more likely? Well, you just proved it. Because this is 15%, this is 13%. That's why it's more likely. Okay, 70. Which one is not true? The mean, median, and mode are equal Or, okay, now averages. So averages is going to fit a normal distribution. So this is a good question on a normal distribution. Here we go. That is the mean, the median, and the mode. So that is true. So that checks out. That's okay. The area under the curve is 1. Yeah, that's true. That checks out. That's okay. The curve never touches the x-axis. That's true. Because there are some crazy Warren Buffetts that live outside. They're outliers. So the curve just kind of gets closer and closer, but never touches it. The curve is skewed to the right, and that's kind of what this wedge shape thing's talking about. Under a normal curve is perfectly symmetrical. So this is the one that's not true. So a normal is always perfectly symmetrical. So perfectly symmetrical means this. That means 50% live here and 50% live here. You found the exact median. Okay, then we skipped 7.2. 7.3 is just using the central limit theorem, so nothing goes up. I mean, nothing really changes. It just says you can illustrate the law of large numbers. That means the larger your sample, the closer it's going to get to the theoretical probability. So the larger the sample, the closer the x bar gets to mu. And that is true. So let's do a couple problems. 87. Okay, 87. They're giving you this data comes from a normal distribution. So the original distribution is given. It's a normal distribution. Looks like the average is 60, standard deviation of 9. Who knows what it's talking about? Suppose that you form random samples of 25 and x bar, let x bar be the random variable of the averages. So we're taking averages. This is capital sigma. This is sum. We didn't do any sums, and they're not going to test you on sums, so don't worry about that. So for part C through F, sketch the graph, shade the region, label, and scale. Okay, here we go. So they kind of walk you through it. So A, sketch the distributions of x and x bar on the same graph. Okay, so x is this. X is 60. And the standard deviation, I probably should give myself some more space. Standard deviation is 9. So let's go 1, 2, 3. 1, 2. There we go. Okay, so we're going to go call that 69, 78, 87. And this is going to be 51. 42, 33. Okay, so here we are. Something like that. So x bar is red. Now I'm going to change, no, x is red. So now if we change to blue, here we go. Let's find this. So x bar is going to be normal. We're going to use the exact same mean, so we're going to start at 60, but your standard deviation is going to be smaller. So we're going to take the old standard deviation and we're going to divide it by the square root of n is 25. So 9 divided by 5. So that is 1.8. Okay, so that means this is 1.8, so I'm going to go that guy, I'll go above it, 61.8, and if I add 61.8 plus 1.8, that is 63.6, and if I add, it's going to be 65.4. So it tightens it up really quite a bit. I mean, our 3 standard deviations did not even fall outside of the first standard deviation on the original Okay, now if we go backwards, it's going to be the same thing. 60 minus 1.8, so we're 58.2. If we minus 1.8, 56.4. And if we go again, minus 1.8, 54.6. So that means this, your curve just shrunk down tremendously. Okay, so now let's answer C. So what is the chance that the average is going to be less than 60? And if you think about it, let's do the calculator to double check, but it should be, I mean, either way, 60 is the dead center. So 50% live on the left, 50% live on the right. So what are the chances that the average is smaller than 60? Well, let's find out. Okay, let's go menu, 6, 5. We're going to inverse. No, we're doing a cumulative. So I want the range. I want the lower bound to be 0. We're going upper bound of 60. The mean is 60. But your standard deviation, what are we using? We're going to use, it was 1.8. Oh, something didn't work. What'd I do? Okay, let's try it again. Menu 6, 5. CDF, let's go 0. Upper bound 60, 60. Sigma, we're using 1.8. And, okay, yep, there we go. Okay, 50. So it worked. Okay, now D, find the 30th percentile. So D is where we're going to do inverse the norm. So let's go menu, 6, 5, inverse normal, and they're telling you the specific area. They wanted the 30th percentile, so 0.3. Your mean is 60, and the standard deviation is 1.8 because we're doing X bar. Hit OK, and that is 59.1. Okay, now let's look right here. So the 30th percentile, 59.1. Okay, so 59.1. Where is it going to be? 56, 58. 59.1 is somewhere in here-ish. Let's see if that makes sense. Okay, so this from the second and third standard deviation, that captures like 13.5% of the population, and this was like 2.35 or something. And then this one, between the mean and the first, that's 34%. So if I got, yeah, that makes sense. That's going to be about 30% of the population. Okay, let's do E. We'll skip F, because if you can do E, you can do F. Okay, now they want the probability of X bar landing somewhere between 56 and 62. So menu 6, 5, that's a cumulative distribution. Let me look here. They wanted the lower bound to be 56, the upper bound to be 62. Standard deviation to be 6, mean to be 60, standard deviation to be 1.8. And holy crap, I did that twice now, so I gotta go menu 6, 5. Boom, boom, boom. Okay, we're going to 56 to 62, 60, 1.8. God, I must be going over and hitting cancel. Menu 6.5. 56, 62. The mean is 60 and 1.8k. Do not hit cancel, hit OK. So 85%. So you got an 85% chance that you're going to land somewhere between 56 and 62. Okay, let's look at the next one. 89. Salaries for teachers in a particular elementary school district are normally distributed with a mean of 44 grand and a standard deviation of 6,500. We randomly surveyed 10 teachers from that district. Okay, there's a huge difference between A and B. Okay. A, you need to find the 90th percentile for an individual teacher's salary. So we're going to use the normal distribution. Okay, 90th percentile, here we go. And on B, we're going to use the central limit theorem. Now we're looking at average teacher's salary. Okay, so we're going to go menu 6.5. We're going to inverse the normal. The area, they want the 90th percentile. The average is 44 grand. And we're going to use the standard deviation from the population, 6,500. And that will give us, so the 90th percentile, so 90% of all teachers make 52 grand or less. Anywhere from, I guess, 0, which is not really reasonable, but 52 grand or less, 52,330. Now, let's do that same thing. Menu 6.5, inverse the normal, let's find 90% of a 44,000 average. Okay, the standard deviation, if you want the average teacher salary, we're going to use 6,500. But you're going to divide that, because you took a sample of 10 teachers, you're going to divide that by the square root of 10. And that's going to be 46. So it's usually always smaller. But the larger your sample, so that n was 10, because that sample was pretty small. I mean, depending on how many teachers are in that district, but if there's 1,000 teachers in that district, and if you sampled half of them, 500, then it would be closer to the actual population. So the larger your sample, the closer you get. So if you have a small sample, your numbers are going to be lower. Okay, let's look at the next one. 95. Okay, this is a good one. This would be a good test question. Your company's got a contract to perform preventative maintenance on thousands of air conditioners in a large city. Based on service records from previous years, the time that a tech spends servicing a unit averages 1 hour. Standard deviation of 1 hour. So, mean is 1, sigma is 1. In the coming week, your company will service a simple random sample of 70 units. So we got n is 70. You plan to budget an average of 1.1 hours per tech to complete the work. Is this going to be enough time? Okay, so this is a pretty tough question. We're going to use central limit theorem. We got a sample of 70 units, so we need to find kind of the average amount time. You're planning on 1.1 hours, so let's do that. You're going to do a normal CDF. We're going to go from 0 to 1.1 hours. We're going to use the same mean as the population mean. We're going to use 1 hour, but your standard deviation, we're going to use 1 divided by square root 70. Boom, 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 boom. Punch that in. When you punch that in, you're going to get 0.7986. Okay, so here's what I mean, this is pretty cool. This is a decent application of how stats are used in business. This is awesome. So that means 80% of the techs will finish anywhere from that range, 0 to 1.1 hours. So you tell your boss, hey, if you're going to average 1.1, so if you're scheduling them to do this many a day, you either overschedule or you underschedule. Well, if your data says 80% of them will finish from anywhere from 0 to 1.1 hours, that's 20% of them are not. So 20% of them are going to fall behind. So you probably want to up this 1.1 hours to something, 1.5, and do it again until you can capture almost everybody. But you don't want to capture, you don't want to schedule too much, because then you'll have them time to kill. They're on the clock with nothing to do. So that's a pretty sweet problem. Okay, last one. 96. Typical adult has an average IQ of 105. Standard deviation of 20. If 20 randomly selected adults are given an IQ, what is the chance that the sample mean will be? So they want this. What is the what's the probability that between 85, that the X bar is going to be between 85 and 125? So it's going to be less than 125, greater than 85. So here we go. That is a normal CDF. The range is 85 to 125. The mean 105. And your standard deviation, you're going to use 20 divided by square root of 20. 20 randomly selected, 20 divided by square root of 20. Is that right? Okie dokie. And that, oh shoot, I don't even know what that is. Let's see what that is. Normal CDF. Okay. Menu 6.5. Okay, lower bound, what do we want? 85, upper bound 125. Average is 105, and sigma is 20 divided by square root of 20. And is that right? Paching. Okay. Holy cow, why is that not working? He wanted you to tell me what the crap's going on. That is super annoying. Alright, let's try it this way. 85, 125. The average is 105. Well, I'm not gonna. Yeah, we can do this. 20 divided by the square root of 20. And paching. 0.9999999. Okay, that's good. So that is 0.999. So that means almost everybody, 100%. So 100% of them will fall between 85 to 125. Okay, that's it for chapter 7.